All right, go ahead.
Okay, so hello everyone. I am Bhavya Ghai. I'm a applied scientist at Amazon New York. Previously, I was a PhD student at Stony Brook University, and this work I did when I was part of the university. So this work, D-bias, is a causality-based human-in-the-loop system for tackling algorithmic bias. This is a joint work with my PhD advisor, Professor Klaus Müller, and I will be happy to take any questions in the middle if you have them. So let's get right in. And by the way, this paper was accepted at IEEE with 2022. So I gave a talk on this paper last year. I'm happy to talk about this more today. So let's first talk about algorithmic bias. So algorithmic bias occurs when computer systems discriminate based on an individual's inherent characteristic like gender or acquired traits such as nationality that are protected classes under law and are irrelevant to the decision-making process. By the way, there are a whole bunch of definitions out there for algorithmic bias. This is just my definition of algorithmic bias. So if we look at a typical ML pipeline, so this is how bias manifests itself in one particular way. So let's say the real world has some kinds of social biases based on gender, race, etc. These biases are propagated to the data sets, which are then passed on to the ML model. And the ML model then shows these biases in its outputs where it treats different population groups differently. There are multiple real-world examples of algorithmic bias, which includes Compass recidivism prediction algorithm, Amazon's recruitment algorithm, Red Bull's policing algorithm, etc. So algorithmic bias has been termed as an imminent AI danger, which impacts millions daily. More recently, we have seen a lot of coverage of algorithmic bias in the media. There have been a whole bunch of uh, media coverage talking about different companies and different kind of algorithms like classification algorithms or recommender systems or facial recognition algorithms, etc. The key takeaway here is that bias is a real AI danger and should focus on bias as an imminent AI problem. Based on all this media coverage and the real world examples of bias, there have been some follow up in the in the literature as well. There have been different algorithmic solutions as well as visual tools aimed to tackle algorithmic bias. This work is based more on the visual tool side of things. So I'm talking about the existing visual tools in this space already. Some of them include Silva, word bias, fairwiz, discrelence, fairsight, fair rank quiz. All of these visual tools are aimed at tackling algorithmic bias in one way or the other. The key point here is that most of these tools are focused on detecting social biases and not mitigating them. There are a couple of tools, I guess, in these existing ones that talk about mitigation, but the mitigation is pretty basic for these tools. In this particular work, the bias that I'll talk about today will go much further in how we can come up with a much more sophisticated human in the loop debiasing algorithm. So this work, the bias relates most closely with this first tool here, that is Silva, because this tool also uses a causal network in the interface. So, but again, this tool Silva is only limited to bias detection and not mitigation. So our tool goes a step further in doing that. Now let's talk about debias. So debias is a visual interactive tool that embodies human-centered AI approach for algorithmic bias detection and mitigation. If we look at a typical machine learning pipeline where we have raw data, which is fed into a machine learning model, and then there are some outcomes, debias operates on the raw data stage, where it takes in the raw data, it audits for different kind of bias, and then it generates a debiased data set, which can be fed into the machine learning model to get more fairer outcomes. So debias relies on causal models to present the underlying patterns in the dataset. If the dataset contains social biases, they will also be reflected in the causal network. And then in step 2, causal models also help incorporate the domain knowledge to simulate the debiased dataset. So this picture right here shows the workflow of the entire tool. At stage 1, we have the raw data coming in and we try to generate a debiased causal model. At stage 2, we try to get to a refined causal model. This human refining here in this step is because the default causal models are not perfect, so we need a human to get to a refined causal model. In stage 3, we use human refining again to identify and tackle the undesirable causal relations. And in step 4, we use the debiased causal model to generate the debiased dataset. In the coming slides, I will go over each of these stages in much more detail. So let's look at stage 1, that is create a causal network. So causal modeling and inference is, by the way, a whole domain in itself. Here, I'm trying to use causal modeling for the application of fairness. Okay, so let's say we have some kind of raw multi-weight data coming in. Here, each column is a different feature and each row may be a particular sample. Here, let's say S might be some kind of sensitive attribute, let's say gender, race, or something, and Y might be an outcome variable, let's say getting a job or getting a loan application or things on those lines. So we use a PC algorithm, which is a causal inference algorithm to generate a causal DAG. So what is a PC algorithm? PC algorithm is a causal discovery algorithm that provides qualitative information about the presence of causal relations between different columns in a dataset. So here, the causal DAG that you are seeing, each node in the causal DAG is a column in the original data set, right? And each edge here represents a causal relation. So if there is an edge between, let's say, the nodes S and Q, it means that S is S, the node S causally impacts the value of S, there will be a change in the value of Q. That is what it means by being a causal relation, but not the other way around, because causal edges are directional. So here we only got qualitative information, whether a causal edge exists or does not exist between any two nodes. The second step is to get quantitative information to estimate the strength of each causal relation. For that, we use something called as a structural equation model. A structural equation modeling is a generalized modeling framework that helps estimate the strength of each causal relationship. Here, structural equation modeling can use any kind of linear or non-linear modeling techniques, but for the interest of interpretability, here we have used linear models to estimate the strength. In other words, we can think of it as a bunch of regressions where each node is modeled as a linear function of its parent nodes. For example, the node Y might be modeled as a function of its parent nodes, that is P, Q, and R. Okay, and here the betas are the regression coefficient. So the strength of each causal relation is defined by the standardized beta coefficient. So the default causal network that we got here in step 1 might be imperfect because of the limitations of the causal discovery algorithms. Defining causal is a very hard problem, and despite the recent advances, the current causal discovery algorithms are not perfect. So we need some kind of human refining to get to the final stage. Okay. But now we'll first see this stage in the tool itself. Okay. So this is the visual interface of the device tool in general. Okay. So we have this left side panel, we have the central panel, and the right side panel. Currently, we will just look at how to create the default causal network in this kind of interface. So we first start with choosing a data set. Then we go and choose the label or the outcome variable. Thereafter, we choose all the categorical variables in the dataset. And finally, we click on the causal model button. When you click on the causal model button at the back end, PC algorithm and structural equation models are executed, which generates this kind of a causal network in the middle panel that you can see. So here, as I said, right, each node represents a column in the dataset, and each edge represents a causal relationship. Here, some edges are green in color, some are orange, some are red. They represents the sign of the regression coefficient. So the if there is a positive if positive regression coefficient, that edge is coded in green color. If the coefficient is negative, we use red. And if there is we if the PC algorithm could not determine that direction of the causal edge, they are in orange color. If you see clearly, right, the edges in orange color don't have any arrow on them because those edges are undirected, because the causal discovery algorithm could not determine that direction for those causal edges. So now we'll move on to stage two. We will try to get over some of these limitations. So step two is refining the causal model, right? So as I just mentioned, that orange edge represents the undirected edge, red is negative beta coefficient, and green is positive beta coefficient, right? So now what we'll do is we'll try to use human refining to get to the refined causal model. As a domain expert, we can determine what is the direction of a given causal edge. So we can try and click on each of these orange edges and direct them based on our own domain knowledge. And similarly, we can also act upon an edge if we feel that the direction of that edge is misrepresented. For example, in the causal network on the left-hand side, we can see that it shows that marital status is causally impacting gender. However, we know that gender is something which cannot which cannot be determined by a marital status, because in causality, there is a sequence to things, right? So something that happens later cannot impact something in the past. So in this case, it can only be the case that gender can impact marital status and not the other way around. So we, in this, on the right hand side, we change the direction of that causal relation. Similarly, if you look at other orange edges, let's say the edge between hours per week and income, we find that here that edge was orange because the causal model could not determine the direction. But on the right hand side, we direct that edge from hours per week to income, because from a real world knowledge, we know that hours per week can impact the income and not the other way around. Similarly, if we look at the edge between education and income, we again see that education can impact income, but not the other way around. So on those lines, we try and use our domain knowledge to get to a refined causal model by acting on the undirected edges or changing the erroneous causal edges. So device supports operations like directing, deleting, reversing edges for the refining process. We'll look at again that in this example. So here we see that gender and major. The major here means the college major. Okay, so we choose the direction from gender to major because the time of choosing a college major comes much later than your birth, right? So here we choose the direction from gender to major. By the way, here I'm assuming gender is something that we know at the birth time, and I know they can be different for different people. Similarly, when you look at age and work experience, in the original causal lag, it was orange edge, but now I change to green because we know that age can impact work experience. Let's say more age might mean more work experience, but not the other way around. So now let's go for the third stage, which is auditing for social biases. Once we have a refined causal model, we can now try to identify social biases, and there are three ways in which device supports this process. First is via the mean of exploratory visual analysis. So device supports a whole bunch of visual charts which shows the univariate or bivariate distribution between different columns to show if there is any disparity or not. For example, here the first chart here, the top one here, shows the distribution between gender and income, and we find that the proportion of females who earn more than 50K is much less than compared to male. So it means that there is some disparity in the data set that we are seeing here. Similarly, the chart at the bottom right It again shows the same thing, but in a four-fold display plot. Here we see that 12% of females make more than 50K, although 31% of males make more than 50K. So there's a big disparity between the two. So this is one way to show if there is disparity or not between different variables, or if there is sampling bias. If let's say we plot the univariate distribution and we find that there are much more females than males, or there are much more of one race than the other. So it can also show sampling bias, and it can also show some kind of disparity in numbers. Second is we use a whole bunch of conventional fairness metrics to show bias. So this includes things like parity difference, individual bias, accuracy difference, false negative rate difference, false positive rate difference, etc. So these are something that you will find in typical machine learning literature to quantify bias. We have used also a bunch of them to give a more comprehensive view of bias in a particular data set. And lastly, we use causal analysis to show bias. So debias computes all paths, all causal paths from the sensitive attribute to the outcome variable to uncover any direct or indirect discrimination. So let's say in this particular diagram, if you look at the edge, the node gender and the outcome variable income, we find that there are multiple causal paths that connect these two nodes. This shows some kind of indirect discrimination because there is an indirect effect of gender to the outcome variable. For example, gender is here shown to influence hours per week, and then hours per week is shown to influence income. So there is an indirect effect from gender to income. And in case there was a direct edge between gender and income, let's say, in that case, we would have called it direct discrimination or disparate treatment. And this kind of indirect discrimination is called disparate impact, where there's a proxy variable involved or multiple proxy variables involved that indirectly have an influence on the outcome variable. So again, let's look at this in the tool itself. So we just talk about here, I think, of the third case, the causal analysis part. So the user can choose the source from here, let's say gender, and the target as job. And when you click on find paths, it shows all the paths from the sensitive to the outcome variable. When you click on any of those paths, it highlights that particular path in the causal DAG for you to see exactly how it works out. Okay, so now that we have talked about creating a causal network, defining a causal model, then try to identify identify biases in the data set. Now we'll finally talk about how to mitigate these biases. Yeah. So for debiasing, a user first needs to identify the undesirable causal relations and then act on them by weakening or deleting those edges. So let's say this is an example of a refined causal model. Here, based on our own domain knowledge, which may be subjective based on an individual, we might think of certain edges as undesirable. For example, here I might perceive as the causal edge between gender and hours per week to be undesirable. In other words, I have this assumption or worldview that gender should have no role to play when it comes to hours per week. Or, for example, I might think of the causal edge between gender and work class to be undesirable based on my worldview that there should be no role in which work class males or females work in. So I can choose all of those edges in the first part to just identify which are the undesirable ones and then act on them by deleting them altogether. Let's say in this case, I remove these three edges that I feel are undesirable. When I do these operations, I get to what I call as the debiased causal model. As you can see on the picture on the right, all the three causal edges are not there anymore, which were there on the left-hand side, right? So what will happen is when I do these kind of operations, that's the debiased causal model. I get the debiased causal model, and then the system will generate a debiased data set based on the resulting debiased causal model. You can imagine a causal model as a data generating mechanism. So when you have a causal model, you can try and generate as many samples as you want based on this as the underlying data generating mechanism. So when I operate on the causal model, I'm basically changing that data generating mechanism in a way. So now what I have is a more fairer debiased causal model, or a more fairer way to generate a debiased data set. So our intuition here is that data set that we get from this debiased causal model will be more fair. But then how do we simulate the debiased data set from the debiased causal model? We'll talk about that in the coming slide. So let's see how it happens in using a toy example. Okay. Let's say we have on this left side a refined causal model. And in this refined causal model, we thought that the causal edge between S and Q is undesirable. So we removed that edge altogether to get to the debiased causal model here, right? Now, what we do is we first compute the set of nodes that are impacted by the user interaction. In this case, the user has dealt with one edge that is between S and Q, right? So the set of nodes that are impacted by this interaction is the target node Q and all of its children nodes. In this case, that is just Y. So as you can see in this picture here, I have highlighted two nodes, Q and Y, which are impacted by user interaction. All other nodes, that is apart from Q and Y, are not impacted by user interaction. So to minimize data distortion, we will simply copy the rest of the nodes, that is S, P, and R, as it is to the debiased data set. As you can see here, S, P, and R are left untouched, okay, because they are not impacted by user interaction. Now for each impacted node, that is in this case Q and Y, we will generate their new value using a weighted combination of its parent nodes, the intercept term, and a random term. So here we looked at that we modeled each node as a function of its parent nodes, right? A linear function of parent nodes. So what we do is here we propose this new term in the equation that adds randomness or more fairness to the whole data generating mechanism. And this alpha here represents the degree of change that the user has gone through. So if let's say a user removes an edge altogether, then this alpha will become 0. So basically here in the first node, in the first term, alpha will become 0, and this random term will take a major role in the process. Or if the user chooses to dilute the edge by 50%, then alpha will become 0.5 or 0.25 if it is 25%, and so on. This is a novel new term that we've added in the process, and we have talked about a lot of these technical details in the paper. So I will not talk about them here, but you can see the paper for more details. So once we get these new values for the impacted nodes, that is Q and Y, we rescale the generated variable so that its distribution is close to the original distribution. So our main agenda here is that we want to minimize data distortion and enhance fairness. And as I just said, you can go and see the paper for more details on how these things are actually performed. How do we generate the debiased data set, or how do we rescale the categorical variables, and so on. So now let's look at these things in action in the interface itself. So let's say the user finds this edge between gender and job to be undesirable. The user can use this slider to dilute that edge by whatever 25%, or you can just choose this button and say delete edge altogether. When you delete the edge altogether, the system simulates a new dataset at the backend, and you can find here that there are whole different metrics here on the right hand side. The top one says utility metrics, that is the F1 score and accuracy. Then you have a bias metrics that I told about: parity difference, individual bias, accuracy difference, FNR difference, FPR difference, and so on. And then you have at the last donut chart, which shows data distortion, right? So we removed an edge between gender and job, right? So we find the impact of that change on all of these different metrics here. The blue bars here represents the baseline case, and the orange is the one that we have the debiased version. So we can see, right, that after we remove the edge between gender and job, for all the bias metrics, the orange bars are smaller in length compared to the blue bars. It means that the this change has positively impacted all the bias metrics. So we have now created more fairness than what there was before. Because of this change, there has been 2% data distortion, because as you will make more and more changes, you will keep doing more and more data distortion, of course, right? So we want to make sure that we make minimal changes. And at the top, we see that the effort score and accuracy are kind of same, which is a good thing because it shows that because of this change, we do not sacrifice too much on the F1 score and accuracy. If we look at here on these two four-fold displays, the top one here shows original data and at the bottom shows de-biased data. Okay. So in the beginning, what we had was that 15% of females got the job in the original data compared to 26% for males. After we made this change and the system got a new debiased data set out, at the bottom we find that the number of females increased from 15 to 19 and males came down a bit from 26 to 25. Overall, if we look at the disparity between males and females, at the top it was 26 minus 15, that is 11%. Now it came down to 6%. There's an improvement in disparity because of the change that we made. And we can, of course, if we find that the change is not desirable in terms of the outcome metrics, we can go back and again undo that change in the causal model and get the same numbers again back. So again, we can do other things as well. We can also remove other other edges as well, and we can keep on playing with the system to get different numbers. At the last, we click on this debias, and it gives you a CSV file which you can now use for your any machine learning model to get more fairer outcomes. For evaluation, we had two different objectives. One was the ML-centric evaluation, and one is the human-centric evaluation. For the ML-centric stuff, we use metrics like accuracy, F1 score. For distortion, we use Gower distance. For fairness, we use all these 5 different fairness metrics. For human-centric stuff, we use metrics like trust, accountability, interpretability, usability, and cognitive workload. So in the paper, I have shown 2 case studies. For one is for the adult income data set that you can see in the picture now, and the other one I showed is for the Compass data set again. So you can see the paper for more details. Here I'll just talk about the results. So if you look at the numbers here in this table, I have shown 3 different data sets here, and we have chosen sensitive attribute as gender and gender for the first 2 and race for the Compass data set. I've used different ML models here intentionally to show that our approach works for different ML models as well. And here we see the baseline numbers and the debiased version numbers, top and bottom for all these different data sets. What we find is that accuracy is more or less the same before and after this operation. So it shows that the accuracy is not sacrificed too much. And of course, because we made some changes, so there is some data distortion, which is expected. But it is not too much. It's like 6%, 12%, 13%, so not too much. But again, we find a whole bunch of improvements across different metrics. They're very, very significant. If you look at these numbers, you will find that the fairness numbers have come down drastically for many of these metrics for a little bit of data distortion. So we can overall say that debias helps enhance fairness. It preserves accuracy for a small data distortion. And when it comes to the user study, what we did was we had 10 study participants and we conducted a within subject study where we showed them the debias tool and then a baseline tool. The baseline tool here mimics the design of the debias tool, but it has the workflow of an automated debiasing tool. So here in the baseline tool, the user do not see the causal network. They do not make any change to the causal network. They just click on a button that says debias and evaluate, and the system automatically gets some numbers out like you will get for a automated debiasing tool. So we were trying to see whether human-centered tool versus an automated debiasing tool has any benefits when it comes to human-centered evaluation. So and then in the end, we measure things like usability, accountability, trust, and those kind of things. And what we found is that compared to the automated debiasing tool, our tool performs better when it comes to trust, as we can see here, when it comes to accountability, as we can see here, and when it comes to interpretability also. However, on workload and usability, the automated tool works better, as we can expect, right? Because an automated tool does not involve too much work to be done on the part of the user. So there is much less workload. And if you just click few buttons, then you get the outcome. So it is much more usable. Having said that, because the user has a much more dominant role to play in the debias tool, hence the user feels more accountable for the outcomes that come out. Hence, we have much more accountability than the automated version. And we can see exactly how the causal relations work in the data set. So there is much more interpretability as well for the debias tool. And when you have more accountability, more interpretability, you have more human control. So the people felt more in charge, and hence they could trust the outcomes more because they know where they are coming from, how the outcomes came here, and they could influence the changes as well. So they felt more trust in the results as well that we can see. So device performs better on interpretability, accountability, and trust. In conclusion, we presented an end-to-end interactive visual tool for bias identification and mitigation in tabular datasets. We showed the effectiveness of our tool in reducing bias using 3 different datasets. Using a user study, we showed how our tool outperforms automated approaches on human-centric measures like trust, interpretability, and accountability. Very important point here is that involving a human in the loop can be a double-edged sword. On one hand, it provides real-world domain knowledge and fosters accountability and trust. But on the other hand, it can also be its main weakness because the human operating the tool can intentionally or unconsciously inject their own biases as well. In the paper, I have shown a case where our tool can be misused by a malicious user to exacerbate the bias even more than what it was before. The objective of our tool was to give as much flexibility as possible. So here we are assuming that the person using the tool is a very responsible person. But if there is a malicious person in charge, then it can also do much worse than what it was in the beginning. And in the future, we'll want to extend this approach, this human in the loop approach, to tackle biases from word embeddings as well. And by the way, we can also, anybody can play with the tool live. There's a demo on my own webpage. You can go and check it out and play with this tool as well. With that, I thank you all for your attention, and I'll be really happy to take any questions. Thank you.